People, welcome to the final monthly meeting of the Royal Astronomical Society of Canada Victoria Centre meeting for the season. And thank you so much for coming out on this beautiful night. It's lovely to stay outside. You can smell all the flowers and everything, but just shows you that we've got a real dedicated crew and hard talkings tonight. So our program, I don't know if we have any old news, but we have some announcements, upcoming events, and our guest speaker tonight, which I'm really looking forward to, is Matt Williams, who's giving a talk on going interstellar. When and how will we travel to the nearest stars? This might not occur within our lifetime. and after the talk, we're going to everyone's welcome to go up to the fourth floor of the Elliott Building for coffee, tea, cookies, and conversation. So the first thing, announcements. I am the President Reg and the acting Vice President, and also the acting outreach captain, and I have nothing to say.
How many Galileo moments?
And the news editor, Sky News editor Bruce has just released another fabulous issue. I hope you might not have had a chance to read it all. But there's a terrific article on big aperture, on aperture fever, part 2. And there's also a wonderful interview with Mr. Jim Hester, which I found fascinating. So if you've got a moment, check it out. And we'll say, Bruce, do you have a few words to say about your latest issue?
Pretty much just Palomar is going to be probably featured in a couple more articles to come. Originally, I wanted to really focus on Russell Porter. Even before I took on Sky News, it was in my idea to do a story on this. He's pretty much the father of modern amateur astronomy when you consider what happened at Stellarfade and the resulting international media storm that hit the amateur community. Basically, that switched from the old guy with the rich guy with basically the brass instrument brought over from London to middle class workers who were basically building their own telescopes. A huge change. Probably as big a change as what happened in the 90s with the industrial process of telescopes. Those people that were just slack like me would make their telescopes.
Well, great work. Keep it up. I look forward to the next historical issue.
One more left.
Okay, our treasurer, Deb.
We have, as of this morning, $13,149.32 in the account. But as of this evening, we have $1,006.47 with outstanding checks. So we have just over $12.
Okay, thank you for that. Chris, our membership manager, is not here tonight, but he sent me an email. We have currently 285 members and about 22 on the grace period delinquent list who have to pay up or they're dropping out of the club, which is kind of a normal value. I've got down here the Astronomy Day team captain, David Lee, but Astronomy Day is kind of wrapped up, but he's heavily involved in other things. Do you have anything to add tonight, Dave?
Yeah, we're busy doing scheduling for the Saturday nights of the day. I guess the big deal will be in July when we have the big lunar landing celebration. So it's pretty full with a lot of speakers, which should be really good. And I think the week of the July 20th, there's additional speakers going to be.
Yes. And but David is also involved in arranging a moon-themed exhibit for the Bruce Hutchison Library.
That's
Is that correct?
Yes.
So we will be doing that in early,
Early July.
that should be kind of a fun event, seeing that thing out.
Everybody bring their old stuff.
Yeah,
Come and see me in the library. I have a book for you.
Oh, that would be good.
Yeah.
okay.
I don't know where my copy is right now.
So, the school program, Sid,
School program is almost over. I don't have any much more to add to from the last month's meeting, except I tallied the distance travel back and forth to the school. It was fun to find out how far away Lori and I have gone to. We have gone to Calgary and back 2 times. So it was a quite interesting trip going there. And, yeah, so we had 90 presentations, and we started in September. So,
I think we should shut that out again. 90 classroom presentations.
yes, correct.
That's a pretty remarkable number.
And we had 3. And we had 3 night study viewing at 3 different schools, and it was well attended. One of them with proud, thank you,
Yeah.
at Mill Street Elementary School. Thanks for your help, and thanks for all the volunteers who were able to help. Thank you.
That was a lovely evening there.
Yeah.
Thank you, Sid. Technical committee, Matt.
We received in the mail the second piece that we needed for that pollinating telescope, the Takahashi. So Dan and I are on schedule to go up tomorrow evening. Anyone who wishes to join us can. It'll be pretty boring. But we're gonna see what it tells us about what next steps we need to take. As well, we're in discussion with OPT, Larry at OPT. He's giving us his best advice for what we can do to resolve the issue with our telescope's collimation.
Okay, good work. So Matt mentioned a device, Takahashi device. It's an alternative way of trying to collimate the telescope versus the other system that we've been trying. So we'll give that a try. It'll be interesting to see how that works. And hopefully we'll have that up and running again soon. Website, Joe.
No report.
Thank you.
Thanks.
Michelle is not here, so no observing report. And Nelson is flying out to the center of the universe, Toronto, for the General Assembly at this time. He sends us his regrets, but he has no report. And I see that there's a little bit of cut and paste here because I can see a reference to science fair winners. I would like to say that with our participation in the science fair, and it's largely Dorothy and you're involved.
Lori. Bruce, what you were involved with?
Bruce.
Well, and Lori, yes.
Lori is involved, and David, you've been involved as well. We recruited 2 very active members through that process, so it just shows you the value of doing that. So we've got 2 young members who are in both grade 6, grade 7 level of bringing scopes up to the hill, and are really very engaged in our club. So it's a really great program. All right then, upcoming events. One that some of you might not be aware of is that we have a 20-inch Dobsonian telescope that we used to be at the Victoria Centre Observatory, and we've moved it down to the center of the universe. And we get a good look at it, and the mirror needs some cleaning. So Bill Weir has offered to clean the scope, so he's going to take the mirror out on Friday afternoon at 2 o'clock up at the center of the universe. And I thought it might be useful. Some other people might want to know how a technique to wash their mirror. So we're having a mirror washing clinic up there at 2 o'clock. Everyone's welcome to come up. The gate's open. There's no problem getting up there. And I'm quite interested to see how that works and how much it cleans up the scope. Yes?
Any chance that can be videotaped for those of us who can't make it?
You know,
Yeah,
he
good
is,
question, good point.
I don't know if we can do that, but what he has done is sent me a videotape that he learned how to do it, so maybe we can send that out in case. But he says it's pretty simple to do. Some people use the cotton swabs to clean it, and he's proponent, use your bare hand because your hands are very sensitive, and if they run into a bit of grit, they know when to stop and get it off in a different way. So that'd be interesting to see how well that works. The other thing, the other big news is at the VCO, we have 2 new zero gravity chairs. These are to allow you to sit back in comfort and watch meteor showers or kick way back and look at the zenith. A lot of people's necks no longer swivel, and this is a great opportunity to use that system. So they haven't been unboxed yet. They're in the room where the 20-inch obsession is, but it could be fun driving those things, so that'll be a highlight. Our Saturday star parties continue on. We've scheduled 22 altogether, and they continue right through every Saturday evening until September 7th. And Margie has just sent out another notice to recruit people to sit at our welcome table and greet people in the center of the universe. It's kind of a fun job. She's very organized, and she's written up a lovely set of instructions how to set it up if you're not too sure. So please give that consideration and drop her an email if you're interested. Now, I mentioned the RASC General Assembly, June 13 to 17. Before I do, I want to go back to the star parties. We did have a problem with the dome at the 72-inch plastic telescope, and it is now in operation again, so that's a great victory. But the dome for the 16-inch scope is still jammed, so there was a bit of a dome epidemic up there this season. So things are on the uptake. There's one thing here, a torrid resonant swarm. Now, I didn't know anything about this, and then our treasurer sent me an email about this story, and I was traumatized. And I said, what is this thing? A torrid resonant swarm. Well, some of you might know that Peter Brown and David Clark are kind of leaders in meteor shower studies and things like that. And they just wrote a paper about the latest, the 2019 torrid meteor shower is interesting in that we're coming very close to what they call a ribbon of rocks, dangerous rocks indeed, associated with Comet Enki. This comet apparently they feel broke up about 10 to 20,000 years ago and left a ribbon of fairly large rocks, and they could be dangerous. And these things apparently are on some sort of a resonance with the orbit of Jupiter, so they've done kind of a modeling with it. Now, David Clark said, if we're talking a 100-meter object, we're not talking a civilization destroying event. That's to calm you all down. But we're talking a potential Tunguska ground clearing event over Toronto. So for that reason alone, I canceled going to the GM. So what he's done here is this is a model of one way of this swarm, how it rotates, and I'll try and get this to work. So if you can see, they've got a cluster of bodies that are roughly in the same plane as our planet. It's like going a little bit below it. And you can see this cluster, or swarm that they call, the Earth is going to be flying fairly close to this. So it's quite wonderful, the graphics as they can do and model these things, is it not? But let's say you said, well, that's okay, but what if I'm on Earth? How do I find these things? Well, funny you ask. This is another thing here. This is looking at the night sky. There's the sun. And look near there, there's going to be a horde of these rocks coming towards us, right towards us here. Most of them are going to fly below us. It is conceivable that something could enter the atmosphere. So this is going to mainly take place between somewhere between towards the end of June and through July, because it's spread out a little bit. Yes, Bruce?
Yeah, the peak is June 28th, which is also a VCO observing night on Friday. And you still got your Skylab helmets. I wrote a little piece up during last, I think the closing part, so it's in the back of the Skylab about it. We don't know exactly how dense it is right now. It's like 92, 22, a lot of bigger stuff. So when we get close enough till it's too late, we'll know what we've got. That's essentially what science is going to bring us.
Well, it seems.
Yeah. But it's like a week ago was when we started the time when we couldn't get hit by something.
Okay.
A week ago.
Well, we made it this
So
far.
weeks, yes.
So good. But it seems to me like the zero gravity chairs were required just in time to see what's going to hit us.
Small party standard.
The next thing is a thing called the International Astronomy Union, which is 100 years old this year, is having all sorts of events, and one of them is on the moon again. And there's going to be an absolute blitz of talks about Apollo and all this sort of thing. And one of the things on the Friday night of July 12th, they're organizing kind of viewing parties for all around the world. And the reason for that is that the moon does not rise until 11 o'clock at night. And during the official ceremony on the 20th of July. So on July 12th, we're probably going to organize a very low-key event where maybe some RASC people will take their telescopes down to Cattle Point. If people want to come and watch it, it'll be good. Because the moon will be about 86% illuminated at the time, but there'll be a nice terminator, and it'll be rising about 7:30 in the evening. The terminator will be, or the meridian crossing will be closer to about midnight or something like that. And then the Apollo Festival, this is growing. It was supposed to be just on the 20th, which coincides to our Saturday night star party. But they've got a bunch of speakers lined up, and I think they're going back starting about midweek. They're going to have different events up at the center of the universe. So it could be quite a fun evening to celebrate the Apollo mission. And on the 20th, the actual day, they're going to run the complete moonwalk video up there. And Chris Gaynor, who's kind of heavy into this stuff, is going to give some talks, comments along the way. So it should be a fun event. The other, after that's over, the next big deal is the Sandwich Fair, Labor Day weekend. And this also coincides with the Cowichan Valley Bright Angel Star Party. So some people might want to go to that. And we have a council meeting on September 4th, and then we're back at Astro Cafe, opens its doors on September 9th. And I've just been written a check for the rent for next year. We've got it all booked, we're all set, the insurance has been ordered. So we're online for that. And the next monthly meeting is in this room, will be on September 11th. And I'm still struggling to get a speaker for that. And then we have the Victoria Center Star Party, September 27th to 29th, and that's out at St. Stephen's Anglican Church, out in beautiful valley in central Sandwich. Just going there and sitting back and relaxing does your work with good. So I hope you can make that. So that's enough now. So this is, we still need volunteers. David Lee pioneered the concept of having a team captain to lead the charge for our astronomy day session. And that model worked quite well. For Sandwich Fair, Lori Roche normally organizes it, but she will not be in that weekend. So what we might do is she's willing to kind of set it up and show somebody the ropes, but we need somebody to step forward as team captain for that. And then the Victoria Center Star Party, Bruce has kind of stepped in there and said he would like to do it, but he's very busy writing his historical novels about astronomy, and I think that he needs some help. So I would appreciate it if somebody would get some consideration and maybe volunteers to be the team captain for that. And then finally, the annual general meeting normally is held in November, but this year it's going to be bumped over to 2020, so it's a long way off, and if somebody would like to help make the arrangements for that, we've already booked the hall, and I don't think it's too much involved in it, we just have to get somebody to help make it happen. So that's my plea for you. So that's the end of my stuff here. So it's now my opportunity to invite Matt Williams to we're going to set up his computer.
Rich, while you're setting up time, just to be sure everybody is aware, Quirks and Quarks this weekend, they taped a panel discussion on human exploration in space, the pros and cons. 4 panelists, including Bob McDonald led it, that the astronaut, Chris Hadfield.
Oh.
And it's really good. CPC made the taping available Wednesday, Tuesday, yesterday. Anyways, it's a really good program, and I think it will really fit in well with it.
This is great, because Matt is actually a professional writer, and he writes all sorts of science articles for a variety of publications, including Universe Today, Interesting Engineering. And he's had articles featured in Physics Org, Popular Mechanics, Business Insider, Gizmodo, and he presented a whole pile of topics. One of them was on interstellar travel, and I've been kind of concerned with all of the efforts and focus on exoplanets. People are seeming to get the attitude is that once we screw up our planet, we can just go down the road to another one. So Matt is going to tell us how to do it. Get it. You got your computer.
Yeah, save the world.
Excuse me.
Right.
I think we are only on the way to the street.
Now, was that not seamless? Thanks very much, man.
Yeah, am I coming through okay?
Yeah.
All right, so. Yeah, okay. Well, actually, thank you, Rich. I want to, you just remind me of something there. A short while ago, my wife and I had the honor of going to talk hosted by National Geographic, which was hosted by Kobe Boykins, who is one of NASA's chief engineers at the Jet Propulsion Laboratory, and he was talking about Mars exploration and Mars exploration rovers. And of course, someone got up and asked him about, have you heard of James Lovelock and the book, The Greening of Mars, and all this business about terraforming Mars and so forth. And he had an opinion on that. He said, human beings need to focus on living here before they contemplate going there. I disagree with him on that one, only because, yeah, it's like this. That's a very respectable position to take there. It's we need to focus on saving Earth. It's not really an and/or situation. At least that's my feeling. That's what Elon Musk has said, and Stephen Hawking said that it may be out of necessity that we will go to Mars and set up shop there. But of course, we cannot let that you get it into our heads there that we've got other planets to mess up, because the amount of time it would take to colonize a planet like Mars, or even longer to terraform it to any degree, we're talking centuries or millennia. And as for interstellar space travel, it's like we can't allow that to let us think that we've got other planets that we can just go up to, because, well, this century could make or break human civilization, and we just don't have that kind of time ready to put our bets on interstellar travel. But it is a very fascinating topic, and it's one that's becoming all the more relevant, in part because of exoplanet studies. And it's one that has been around, the idea of it. It's been around for almost as long as astronomers have understood that the stars are distant stellar objects in the sky, and that other planets, other planetary systems could in fact exist around them. So the idea of visiting them has been there for the longest time. But it's really only been since the 1950s and onwards, with the space age and the Cold War and the space race, that we've really had the ability to contemplate any kind of missions and what they would entail. And as I'm going to get into here, and to sum it up briefly, it's that if you ever want to make an interstellar journey, if you want to consider it, there's two major questions. Number one is, how much time do you have to kill here? And number two is, how much are you willing to spend? So depending on what concept you're talking about, one of those two questions will come up, and chances are one or the other will toss a wet blanket on whatever hopes you've got there, because it's really challenging. So, but to start, humanity actually has been to interstellar space already in the form of robotic missions. We have, it's rather modest, but they do technically fit the bill. Can everybody read this okay? Okay, if anything's not clear, well, font color and pictures, sometimes it's a bit of a struggle to get it all legible. But in any case, the Voyager 1 and 2 probes are now officially both humanity's first successful effort to get to interstellar space, and that's what they were intended for. And in the 1970s and 80s, they explored the outer solar system, and then as of 2018, both had entered the interstellar medium. Voyager 1 in 2012 and Voyager 2 just last year. And in a few more years, they'll be joined by two more spacecraft, which are the Pioneer 10 and 11 craft, which were NASA missions, which were sent out before the Voyager 1 and 2 probes, also to explore the outer solar system. And they discovered very interesting things about Jupiter's moons. And so, yes, I also have a series of dates on when they will reach the nearest star systems. Recently did an article on when Pioneer 10 and 11 would reach the nearest star systems, and which ones they'd be. It's going to be a very long time, however. But nevertheless, all of these missions were intended to enter interstellar space eventually, and it was hoped that someday they would find their way to an extraterrestrial intelligence, to another civilization there, which is why they contained the Pioneer plaque and the Golden Record. And the New Horizons mission, which launched in 2006, it's made a lot of recent news. 2015, it conducted the first flyby with Pluto, and it recently was the first robotic spacecraft to rendezvous with the Kuiper Belt object, which was Ultima Thule. And it was also the fifth to achieve the necessary escape velocity to leave the solar system. So it is expected to reach interstellar space by 2040. So by that time, by mid-century, we'll have 5 spacecraft in interstellar space. However, the amount of time it would take for them to actually get to another star system is, no pun intended, astronomical. And for the Pioneer plaque, it was developed by famous astronomer Carl Sagan and Frank Drake, who is the man who came up with the Drake equation. Is everyone familiar with the Drake equation? Yeah, basic thought experiment on how you can calculate the number of possible extraterrestrial civilizations by just doing the math. How many star systems, how many planetary systems, how many of those could support life. So these, Carl Sagan and Frank Drake were both major advocates of the search for extraterrestrial intelligence. So they created the Pioneer plaque as a as a message to any aliens that would ever find it. And it had, I'm sure people have seen pictures of it there. It has the nude figures of a man and a woman, with the man waving, and it had a symbol that represented the solar system, which was basically a dot in the center with lines drawn out to all the neighboring stars. And at the bottom, it had a representation of the planets around the sun, showing the spacecraft coming from the third planet. So it was basically a message saying, this is us and here's where to find us. And the golden record, which Carl Sagan himself designed with the help of NASA colleagues, that went on the Voyager 1 and 2 spacecraft, and it was even more ambitious. The golden phonograph record that had pictures and sounds of Earth recorded on it, plus directions on the front on how to play it. So this was, it was intended to be either a more detailed message for extraterrestrials or a time capsule in case humanity found it again after thousands of years. In any case, at their current velocity and heading, the Voyager 1 and 2 spacecraft will reach Proxima Centauri in an estimated 16,700 years, that's Voyager 1, number 2 in 20,300 years. And as for Pioneer 10 and 11, they'll actually be heading on slightly different trajectories. So Pioneer 10 won't reach Proxima Centauri, but it has a very good chance of making a flyby of RASC 248 in 33,800 years, whereas Pioneer 11 will make it to Proxima Centauri between the Voyager 1 and 2 craft. So even by even taking the long view, by the time these spacecraft reach any other system, humanity could be long dead. Certainly the current generation would be. So this raises the issue of the biggest challenge in interstellar travel, which is just how absolutely immense the universe is, how much time it would take for us using our current methods to get to even the nearest stars. It would take, it's on the order of centuries or even thousands of years. But there's plenty of excitement about the prospect of doing it, mainly because we found, at present, there are roughly 4,000 confirmed exoplanets that have been discovered, mostly by the Kepler mission. And the nearest was found in 2016 in the closest star to our own, and that's Proxima Centauri. I've got a bit of a funny story about how that announcement came up for us at Universe Today there, but we can circle back. In any case, that was revealed by the European Southern Observatory in 2016. They indicated that they had found the closest orbiting planet to Earth, to our solar system, with 1.3 Earth masses orbiting at 0.05 astronomical units from its star. But given that it orbits a low mass red dwarf star, this puts it right in the habitable zone. So it has an annual cycle there, an 11.2 day orbital period. And at that distance, it's also tidally locked with its star, so any life that it could have on it would be on a day side facing ocean. And multiple studies have been conducted to say, what are the odds of it being habitable in lieu of us actually going there or obtaining detailed spectra from its atmosphere. And so far, it's been a bit hit and miss. Astronomers are sort of divided. Some say, no, it's not possibly habitable. Others saying it could be transiently habitable. Or that there is the possibility life could exist there in aquatic form and basic form. So regardless, we're very eager to start sending missions out there that could actually give us scientific returns in a reasonable amount of time, hopefully while we're still alive. Now this presents all kinds of problems, not the least of which, so shot from Star Wars there, hyperspace. Now, this is one of the problems dealing with science fiction versus science fact. Pretty much every well-known science fiction franchise, they've got some kind of cheat in there for cheating special relativity. They don't accept that the speed of light is a constant or an absolute limit, and, well, they don't get into explanations of physics because they get completely lost. There's no known way in which the speed of light can be circumvented except by completely theoretical and untested methods. And speed of light, roughly 300 million meters per second. We know for a fact that any ship that would want to, any spacecraft that would want to achieve even a fraction of that, would have to have a almost limitless energy source, or just a very, very powerful energy source in order to get up to that speed. So the distance involved, also any mission that we sent out there, there's the issue of cosmic radiation, whether or not human beings could survive what such a long journey like that is unknown, and also things like interstellar dust and debris. We just, again, have no idea what it would involve to get out there. And so, and yes, and all methods that we currently have on the table are either insufficient, or when we're getting into the theoretical or speculative, they're unproven, or they would be prohibitively expensive. But still possible. So to give a little perspective there, using conventional methods, and there are three means through which that we send missions into space right now. And they involve conventional solid propellant rockets, as well. There's also Hall effect thrusters known as ion engines, and also there is a gravity assist method in which you're using either conventional rockets or a Hall effect thruster, and you're picking up a boost by allowing yourself to be slingshot around by a large stellar object, like a gas giant or a star. And the fastest mission to date that did that was the Helios 2 mission. It was sent out in 1979 to study our sun. It used chemical propellants to break orbit from Earth and get within orbit of our sun, and then used the gravity assist to pick up speed, and then was flung out to the other solar system. And it achieved a maximum speed of 240,000 kilometers an hour. That was a record-breaking speed there, but at that speed, using that as a benchmark, it would still take 19,000 years to get to Proxima Centauri. As for a Hall effect thruster, oh yes, sorry, the other issue with chemical rockets is that they're not fuel efficient at all. They burn through their fuel rather quickly and then just basically cruise and are dependent upon gravity to either speed them up, slow them down, or crash them. The Hall effect thruster it's got the benefit of being immensely more fuel efficient. And the basic idea behind that there is that you have an inert gas like xenon, and then it is put through an electromagnetic chamber there, which ionizes it and then uses the resulting ions as the propellant focused through the thruster. Now it's rather slow to pick up speed because it's a small source of power. It's got low specific impulse, but that speed builds up over time. So the Deep Space One mission, which was a technology demonstrator, it achieved a maximum speed of 56,000 kilometers per hour, and that's still 81,000 years to get to Proxima Centauri. Now, these are just robotic missions, though. They were rather small and light compared to anything that would involve people. So if we're dreaming of sending a crewed mission to the nearest star, we have to consult the fastest crewed mission that was ever sent up, and that was the Apollo 10 spacecraft. And it flew to the moon in 1969 without landing. It was the curtain raiser for the Apollo 11 mission, which landed, and it set the record for the highest speed attained by a crewed vehicle, which worked out to 11.08 kilometers per second, or 39,888 kilometers per hour. So it was able to get to the moon in 2 days and 4 hours. And that's highly respectable. But at that speed, we're talking 114,800 years to get to Proxima Centauri. So yes, any human beings that would travel aboard it, a crewed spacecraft that was capable of going that fast, would have to be cryogenically frozen, and by the time they got there, everyone and everything they knew back home would be gone. So, luckily, there are multiple methods to create an interstellar mission there that have been explored, and some of which have even been built and tested. And they include, first I want to, a couple terms to keep in mind. When talking about the amount of energy these concepts could produce, the propulsion concepts, scientists use the term specific impulse, which means the exact amount of energy from a fuel source at minimal cost. So that comes down to kilonewtons per second per kilogram. That's using the standard units that's how it's measured. The other is relativistic speeds, and that means a fraction of the speed of light. So you're going fast enough there that the ship would be experiencing time dilation, time slowing down, and any humans aboard would be experiencing subjective time that was not the same as people who were not traveling with them. So all of these, of course, are rather expensive ideas, but they do have the benefit of working, either in theory or they've actually been tested. So the first is nuclear thermal and nuclear electric propulsion. And this has been explored by NASA and other space agencies as a means of doing short-term missions within the solar system, and even for possible interstellar applications. And it's got all kinds of benefits there. It has a high level of energy in thrust and fuel efficiency to it, so it's got a high specific impulse. Nuclear reactors are a proven technology that have been used for decades. And yeah, in terms of the fuel density it offers, it's virtually unlimited. So in terms of the categories there, nuclear thermal is one, nuclear electric is the other. The nuclear thermal, as the name would imply, it would use radioactive elements like uranium to heat liquid hydrogen or another propellant, and the resulting plasma would be used to generate thrust. A nuclear electric is a bit different. It's kind of like a Hall effect thruster. You have the reactor creating heat, which would then be used to generate electrical energy or to power an electrical engine. So again, you have ionized fuel, which is being charged there by a nuclear reactor. So for all their benefits, because of all these benefits, several design concepts were explored there, especially during the Cold War era. And the one that stands out is the nuclear engine for rocket vehicle application, or the NERVA reactor. And it was a solid core design, so solid uranium core. And it would heat hydrogen fuel in the applications they're exploring. And they even tested the engine on Earth, just the reactor, to see that it could provide stable energy. And yeah, it was able to offer a specific impulse of 5,000 seconds, or 50 kilonewtons per second per kilogram, which was a very, very good turnout there for any missions there that would be conducted throughout the solar system. NASA estimated that with that kind of energy production there, they could send a mission to Mars every 2 years when Mars is at opposition within 90 days. That has any other concept beat by 9 months is estimates I've heard using current technology, and that's what NASA anticipates for their journey to Mars. That's going to be about 9 months. And this could do it in less than 3. But at that same speed, a one-way journey to Alpha Centauri would take 1,000 years. So a very good means for exploring the solar system, not so great with interstellar missions. Another is nuclear pulse propulsion. And this is where things are starting to get a lot more theoretical and rather radically expensive. And this concept too was explored during the Cold War era, but only in theory. And it's a nuclear concept, but one that's a lot faster and a lot more crude. So the idea was originally proposed in 1946 by Stanislaw Lam, who's a Polish-American mathematician, and he participated in the Manhattan Project. So I think you can see where I'm going with this at this point. It's a nuclear concept that was designed by people who helped build the atomic bomb. And they, in 1947, he was joined by Frederick Rains, who's an American physicist, and they did preliminary calculations on whether or not nuclear bombs could propel a spacecraft to relativistic speeds. And they found that, yes, indeed, they could. If you had a ship, I have a picture here. You just scan ahead here. There it is. There's the Orion concept. And the idea is you have a massive ship that holds hundreds or thousands of thermonuclear devices. It drops them out the back of the spacecraft there. They detonate, and then that force collides with a pusher pad at the rear, which then pushes the ship faster. So you're taking the incredible force of a nuclear detonation and you're channeling it into forward momentum. And so the idea is that this would then blast off from Earth using conventional rockets. Once in space, it starts dropping the nukes, detonating them, and they calculated that that could get up to 5% the speed of light. So a mission like that could make it to Proxima Centauri in 20 years. But, as I said, it all comes down to how much you're willing to spend here. In 1968, physicist, the famed physicist Freeman Dyson, a man for whom Dyson spheres are named. Yeah, good. Okay. He did calculations on how big a spacecraft like this would have to be, and he said that minimum 400,000 metric tons to 4 million metric tons, not the least of which 75% of the mass would consist of its payload and nuclear weapons. So to build that kind of spaceship there, in same estimates, he indicated that in 1968 dollars, they could do it for $367 billion. And that works out to about $2.6 trillion today. Which, just for reference there, is about 75% of the United States government's annual revenue. So, similar figures there said that the Apollo program cost about half that, but that was from 1960 to 1975. So, one spaceship, one mission, 3/4 of your annual government revenue if you're the United States. So, not a very good return. The other problem with it was nuclear waste. It would produce a tremendous amount of nuclear waste in its wake, and of course, there were no calculations ever done on what kind of radiation threat the crew would be dealing with, because they're keeping all these nuclear weapons on them, and then they're generating massive clouds of radioactive vapor behind them. The next idea that was explored was a fusion rocket. This is another nuclear power concept there and relies on thermonuclear reactions, but it was a lot more peaceful. And this concept, they called for either deuterium or helium-3 to be used as fuel, and it would be compressed by electron beams until a fusion reaction occurs inside the engine chamber, which would create a tremendous amount of energy in plasma that would be focused by magnetic nozzles and thus achieve thrust. And an example of that is there, which is known as a fusion ramjet, which is similar there. I'll get to that in a second. Anyway, this would have the advantage of fuel efficiency and specific impulse, and could achieve an estimated velocity of 10,600 kilometers per second. Which works out to a one-way trip to Proxima Centauri at that speed would be a little over a century. So again, respectable. Unfortunately, the downside to that is that it too would be immensely expensive to build. The stumbling blocks also include the rarity of helium-3 and deuterium. So they'd have to be mined from other sources there before you could even think to build a ship like this. And second, a lot of progress would need to be made with fusion technology, fusion energy, because the reactions that were driving the spaceship, the energy created would need to be vastly more than the energy needed. And that's something we're still struggling with fusion reactors here on Earth, getting to the break-even point and pushing past it. You need to have a lot more energy being produced versus the energy that's starting the reaction in the first place. And we're still a long way away. So, by the most conservative estimates, a fully fueled fusion spacecraft, as the concepts that were explored, it would reach up to 60 billion metric tons, and once again have a massive bill, an estimated $10.92 trillion. And that's based on estimates of how much money is going towards the development of NASA's Space Launch System. It is a fraction of that weight, and it costs $5.46 billion, so a ship 2,000 times as massive, right? Do the math. Incredibly expensive. The third here is the fusion ramjet, which you see there. Illustration by famed space artist Adrian Mann. This concept was proposed as a way of creating a fusion spacecraft that can provide its own fuel. And the person responsible for coming up with it was Robert W. Buzzard, a physicist in the 1960s, so hence it's called the Buzzard ramjet. So what this does, as you can see from the illustration there, the front of it is a massive funnel from which you've got field lines that are being shown there, and it's part of a magnetic cage that would force fusion from the interstellar medium down into the ship into a tighter and tighter area until fusion occurs with the help of magnetic fields. The reaction then would be channeled in order to create work. And it has the benefit of using fuel obtained from the interstellar medium, which happens to be the most common element in the universe. Unfortunately, in addition to cost, even though by Buzzard's own calculations, a ship like this could reach 4% the speed of light, but it would take quite a while to accelerate up to that speed. So much of the journey would just be spent gathering fuel and accelerating. And yes, it would be very costly to build. Also, scientists have determined since Buzzard's own time there in 1960 that the interstellar medium is a lot less dense than they thought it was back then. So it's not really going to be able to gather as much fuel as was originally hoped. Also, you got the problem of drag. A ship like this is gathering interstellar gas in order to create propulsion and acceleration, but the faster it goes, the more drag it's getting from the interstellar medium as well. So there's all kinds of issues there. But foregoing the idea of speed is now the idea of the concept of the generation ship. And this idea here was explored at length in fiction and with some actual scientific proposals, which I'll get into in a minute. But the basic idea is you create a ship that, forget about velocity, forget about sending a mission in our own time, our own lifetimes, and rather equip a ship and a crew for a very long journey. And it's called a generation ship because multiple generations will be born and die in order. And the original proposal for it there, it predicted a ship that was either powered by nuclear power or a combination of solar energy and hydrogen and oxygen fuel, capable of getting up to 16 kilometers per second in speed, which works out to about 60,000 years to get to Proxima Centauri. But given that you have a ship that's large enough to accommodate a large crew over multiple generations, the time that's spent is really not that much of an issue. And given that you're abandoning the idea of achieving relativistic speeds, it frees up planners there, and who then can focus on the issues of, yes, how big does it need to be? How much supplies are they going to need? How do we deal with the long-term eventualities of a mission like that? But of course, an estimated 10,000 years or more travel time is a very long time for a mission to go. Building a generation ship would be even more expensive than building a fusion ramjet or a fusion craft, because it would have to be able to accommodate hundreds or even thousands of people, multiple generations of them. And also the issues of self-sufficiency, food, water, air, they'd all have to be figured out in advance. Radiation would have to be figured out in advance. A long duration mission like that, the crew would they'd have to account for massive levels of cosmic and solar radiation. On top of that, if you're going to send a ship that's taking thousands of years to get to another star system, there's always the distinct possibility that something much more advanced is going to be invented in the meantime, and it's going to just cruise on by the ship as it's going. So the last possible method that exists that's based on existing technology, and I say this one for last because it is quite possibly the only means the only practical means that exists at present. And that's for what's called directed energy propulsion. And the idea there is you have, similar to a solar sail, you have a light sail, which would be a very large reflective surface there, and it would be towing a spacecraft behind it. You would then accelerate that sail using focused laser arrays instead of just relying on solar wind to allow it to pick up speed. And if in fact the spacecraft is small and lightweight enough, and also it requires no fuel this way, you could accelerate it up to very high speeds, and you could actually send a mission to neighboring stars there in a relatively short amount of time. And this concept was first proposed by Robert Forward in 1948, and he was a physicist at Hughes Aircraft Research Laboratories. And, sorry, did I say 1948? 84. 84? Okay, good. So, yes, he proposed this as a way of freeing up a ship from the burdens of having to carry most of its fuel on it. Because that's the downside to every single spacecraft concept that has ever been proposed. It's that the majority of its mass needs to be fuel in order to achieve the kind of speeds necessary to break free of Earth's gravity, or achieve escape velocity from the solar system, or just get up to fast enough speeds to make an interstellar journey. So such a ship would require no fuel and therefore would be much less massive and could therefore be accelerated to much higher speeds. Also, laser energy doesn't dissipate with distance the same way as solar radiation does, so focused beams would they would be able to keep accelerating it for over a long distance. And the downsides, however, they include the fact that this kind of ship can't navigate itself. If it's accelerated using lasers, it's going to be going at very fast speeds, and it can't turn. It also has to be optimized to deal with interstellar dust and particles, which, if it's traveling at a fraction of the speed of light, could cause some very serious damage to it. So all of that needs to be figured out in advance. You have to plot a course for the ship, design it in such a way that it can withstand any kind of damage, and only then send it on its way. And of course, the cost of developing it and building lasers powerful enough to accelerate it are rather high. But there's actually a few concepts that are in the works there for that very idea, and it is currently our best bet. In terms of how these ideas have been explored over the years, each and every one of the ones mentioned so far, in terms of nuclear thermal and nuclear electric engines, NASA explored them in conjunction with the Los Alamos National Laboratory, where nuclear tests were conducted. They built the NERV reactor, they tested it out. 1972, the program was abandoned, it was defunded because it was the end of the Apollo era at that point. The last Apollo mission would arrive at the moon 1 year later, and budget cuts and the new funding environment required that they basically shelve the ideas. But not only was the technology tested and proven at the time, but more advanced concepts were also designed, which would involve liquid or gas cores, none of which were built. But NASA has taken these plans in recent years and dusted them off, specifically because of the promise they have for interplanetary missions. So, and yes, there is still thought of exploring this technology as a means for an interstellar mission as well. Okay. Project Orion was an attempt to develop a nuclear pulse propulsion. And this was pursued between 1958 and 1963 by Ted Taylor of General Atomics and Freeman Dyson again. So they had worked out the conceptual designs, they had developed all the calculations they needed for how big the ship would need to be, how fast it could get up to. Unfortunately, the project ended in 1963. And the reasons are not entirely clear why it ended, if it was budgets or if it was in fact because the partial test ban treaty, which the United States and Soviet Union agreed to, which put strict limits on nuclear testing in the planet's upper atmosphere in order to limit fallout and, yes, just radioactive waste breaking down on the planet. So this most likely put the kibosh on that research there, because there's no way Project Orion could even begin to accelerate out of Earth's atmosphere unless it could drop nukes that would detonate in the upper atmosphere. Next up, picture here, also by Adrian Mann, is of the Daedalus concept. And that's the concept for a fusion rocket. Now, those large modules you see all around it, that's all propellant. So, and what you see there is also a Saturn V rocket next to it to provide a sense of scale. The Saturn V rockets are what took the Apollo astronauts to the moon. That's how small it is compared to the proposed design. So yes, that gives you an idea of how expensive it would be to build. Nevertheless, between 1973 and 1978, the British Interplanetary Society, they conducted feasibility studies on fusion rockets, and they called it Project Atlas. And specifically, their plan called for the creation of a two-stage unmanned spacecraft that could be used using then current technology and make it to the Barnard star system, which is about 6 light years away within the lifetime of the current generation. And in fact, you can see where the first and second stage meet there. The smaller modules there on top, that's the fuel for the second stage of the spacecraft, where the larger ones power the first stage. So the way this would work is the larger first stage would use up all its fuel over the course of about 2 years, accelerate the spacecraft to 7% the speed of light, and would then detach, sending the second stage, which would then ignite its engines, accelerate itself up to 12% the speed of light over the course of 1.8 years, and then just cruise the rest of the way. And it would cruise for 46 years, thus making the mission there to Barnard Star a one-way trip in a total of 50 years' time. So the technology there on paper looked good. Adjusting that to Proxima Centauri, it would make the same trip in about 36 years. Now, unfortunately, the project was canceled. It was shelved because it was just considered too prohibitive, expensive, and the technology at the time was not advancing fast enough to pick it up. But Icarus Interstellar, an international nonprofit organization made up of volunteer citizen scientists, they formed in 2009 with the express purpose of revitalizing the concept. And so this is one of several concepts actually that they're currently looking into there with the hopes of keeping the dream of interstellar exploration alive. And the Daedalus concept they resurrected as Project Icarus. So their long-term goal is to make this kind of spacecraft feasible sometime in this century. As for generation ships, multiple studies have been conducted. No foundations are currently dedicated to building one, however. At least not directly. It's a concept that's on several organizations' radar. It's not their primary focus. So the first example of a generation ship that was proposed was made by Robert H. Goddard, who is, for whom the NASA's Goddard Space Flight Center is named. And he wrote an essay in 1918 called The Ultimate Migration, which was about future space travel and humanity leaving the solar system when the sun died. And he described them doing this by means of an interstellar arc, where the passengers would be cryogenically frozen for the long journey, but pilots would be awakened at intervals to steer the ship and make corrections. So he's the one who did the preliminary calculations on how long a mission like this would entail, how it would be powered, and that was roughly 60,000 years. And he figured a nuclear power source, if it were invented by this time, because this was 1918 when he wrote this, that was a theoretical concept at the time, unless nuclear power was discovered, a combination of solar energy and hydrogen and oxygen fuel would be sufficient. And yes, that they would have enough supplies and enough space aboard the ship in order to conduct a 60,000-year journey and then be revived once they got there. And in 1928, Russian rocket scientist Konstantin Tchaikovsky, he expanded on this there, and he wrote an essay titled The Future of Earth and Mankind, and he described this further. He called for a Noah's Ark and of a design for which several spaceships would be made, that they would all be self-sufficient. They would have food, water, and air enough to keep a crew in wakeful conditions, and they would make the journey in a few thousand years. Now, the first detailed proposal didn't come along until 1964. That was by Robert Ensman, and he proposed a concept that's now known as an Ensman starship, and I have the image of that right there. This is an artist's representation of it. Now, the Ensman starship relies on fusion power, and that's what the massive black bulb there is at the front there. The vast majority of the ship is is designed to hold fuel and channel the propellant and create propulsion. It's only really in the front section, that very small section there, that the crew would be kept. But the sheer scale of the And what was equally impressive was how detailed his design was. So he called for a deuterium power generation ship, so fusion rocket again. It would measure 600 meters long and have a crew of 200 people, which over time would expand from breeding. And they too would make the journey in several thousand years. And the most recent calculations that were done on the feasibility of a generation ship, and this is someone I had the honor of talking to, and we did a series of articles on the studies, and he produced 3 studies between 2019 and this year, and he used numerical simulation software that he and his colleagues developed himself. The man's name is Dr. Frederick Morin, and he's from the Astronomical Observatory of Strasbourg. And so these 3 studies were dedicated to how large a crew would have to be, what kind of challenges they would face for an interstellar journey of multiple generations and what they would need. And also, even how big the ship itself would need to be in order to have enough interior farmland to grow food. And so he determined from, in the first 2 studies, that a minimum crew of 98 and a maximum of 500, along with a cryogenic bank of sperm, eggs, and embryos, would be needed so that a crew would be able to maintain enough genetic diversity by the time they reached another star system, so that they were healthy and that the odds of genetic diseases being passed on would be minimalized. In his 3rd study, he calculated that the ship would need to measure at minimum 320 meters in length, 224 meters in radius, and contain no less than 450 square meters of artificial land to grow food. So, again, a lot of challenges there. And next up, in terms of directed energy propulsion, this is where, again, perhaps the most lucrative research has been done, because it's really worked out, they've been able to calculate mathematically exactly how much energy and how fast a ship could go. So the first design concept for a light sail was developed by Jeffrey A. Landis from NASA's Institute for Advanced Concepts. And he did a phase 1 concept study in which he said that a sail composed of dielectric thin film could be accelerated up to 330,000 kilometers per second, or 10% the speed of light. And this would be ideal, he said, for, quote, fast transit missions to the outer planets, Kuiper and Oort cloud missions, and interstellar precursor missions. So, in other words, robotic missions to the outer solar system to explore there, and also missions that would go ahead to other star systems to see what's there in advance of any crewed missions. So that kind of mission could make it to Proxima Centauri in about 43 years at that speed. And because this was a phase 1 concept study, that meant that that's the preliminary step, where the math is shown, design concepts are submitted, and if it's considered feasible, it will be carried on. This one wasn't at the time. But a year later, Robert Frisby, who was the director of the NASA Institute for Advanced Propulsion Concept Studies, at NASA JPL, he wrote a similar study on this, and he proposed a light sail that would measure 320 kilometers in diameter. So the light sail itself would have to be very large in order to be steerable and accelerated by lasers. And he estimated that it could be accelerated up to 35% the speed of light and could make the journey in 12 years. He said further though, if you're willing to, if you can build one large enough, if you could get a sail measuring up to 1,000 kilometers in diameter, you can accelerate it even further, up to 47% the speed of light. And it could make the journey in 9 years. And he estimated you need a steady flow, a laser that's extremely powerful that could generate 17,000 terawatts of power. And that's close to what the energy consumes every single day, than what the world consumes in terms of energy. So daily power quota used to fire a single laser for a few minutes. And most recently, and here again I've had the honor of speaking to several of the people who were involved in this project, but in April 2016, Breakthrough Initiatives, a nonprofit organization dedicated to extrasolar missions and search for extraterrestrial intelligence. It was started by Russian billionaire Yuri Milner, and he has recruited such people as Stephen Hawking, Mark Zuckerberg, and I would say a bit more importantly there in terms of those who were doing the calculations, Professor Abraham Loeb of Harvard University and the Harvard Smithsonian Center for Astrophysics, man with multiple positions, many degrees, and he's the chief of the board of directors for what's known as Breakthrough Starshot. And that's their concept for sending an interstellar mission, which would be a light sail and a tiny craft. They also have Professor Philip Lubin of UC Santa Barbara, who is basically the guy when it comes to directed energy propulsion concepts. He's done extensive work for NASA on how to build these missions like that would explore the solar system. And also for asteroid redirect missions, using lasers to bump asteroids. So the idea there is that the spacecraft that would be carried by a rather large light sail would be only about the size of a smartphone, and would be called a wafer craft or the star chip. And it would be a little more than an integrated circuit board there with all kinds of sensors and equipment put on it in the form of microchips. It would also have a guidance system and navigation system and tiny little thrusters, little electron thrusters. So that would be towed by this light sail, and they envision that a 100 gigawatt power laser, much more modest than what the NASA feasibility studies call for, would accelerate this light sail for a few minutes, and it would be able to get it up to a speed of 20% the speed of light, and thus being able to make the journey to Proxima Centauri in 20 years. And the entire purpose of this project, as Abraham Loeb has said to me many times there, it all comes down to in our lifetime. They went with this concept study and they went with this very idea because it's the only way that we could do an interstellar mission within our lifetime. And they have a competitor of sorts, which is Project Dragonfly, and that was the result of the same design study that took place in 2013. So a number of concepts were submitted to the Initiative for Interstellar Studies, and the finalists went to the British Interplanetary Society in 2015 to show off their work. And the Dragonfly concept, which was similar, a light sail, a slightly larger craft with more instruments that could do more studies, it won first place, and the team, who's from the Technical University of Munich, they went off and launched a Kickstarter campaign to get working on their design. The second place team, who was from the University of California, San Diego, and Professor Lubin was one of their consulting people, that got picked up by Breakthrough Initiatives, and that is where Breakthrough Starshot came from. So these two things are now being pursued as a way of making an interstellar mission happen in this century that would also provide scientific returns in the same century. So I myself, I've got a lot of hope for them there. It looks like the best bet. So beyond that,
Before, can you just go back to the
Sure.
previous slide? Is this one here, the Project Dragonfly at the bottom?
yes,
The only one that says it's got a magnetic sail to slow it down on it.
yes,
Well,
Well,
the other systems have that.
yeah. That's true. This was part of their study from the beginning. Breakthrough Starshot, I know, has considered this. They too are looking at all the same ideas and all the math there, trying to figure out how they could slow it down. But Starshot wants to forego the idea of anything that would slow it down, in the hopes of doing a quick flyby Proxima Centauri or a quick flyby Alpha Centauri, slingshotting around the star, and then visiting Proxima Centauri to take photos of Proxima b. Yeah, so that's the big difference. Dragonfly would get there slower, but it would have more sensors, and it would take the time to slow down so it could do more meaningful studies once it gets there. So it's a bit of a balancing act there between speed and scientific returns. But yeah, good eye. I almost drove right over that there. Okay, so these are what is possible using current technology, but of course, people want to know about, well, what could be possible? What is there that's theoretically available, just not yet in existence there? So there are several ideas there. First of which is antimatter rockets. So the basic idea there is that antimatter, basically the antiparticles, they have the same mass but the opposite charge of regular particles. They have been a source of mystery there for scientists as long as they've been studying them. But what is known about them and what presents a good deal of potential is that when you collide an antiparticle with its opposite particle, they annihilate each other and they release a ton of energy. So this idea has been harnessed there for the concept of an antimatter rocket, where hydrogen and antihydrogen particles would be slammed together in a reaction chamber. They would produce as much energy as a thermonuclear bomb, not from single reactions there, but over time, as well as the subatomic particles like pions and muons. And these travel at a fraction of the speed of light. So one concept is to channel those particles, like an ion engine does, channel them through magnetic nozzles and use them as a propellant. Other versions would involve the same antimatter-matter reactions there in order to heat propellant or generate electricity. And these all hold a great deal of promise, at least in theory. The advantages are it's got low rest mass and incredible energy density. And of all Starship concepts, they're theoretical or based on existing technology, this has the most power and fuel efficiency of any concept ever proposed, pound for pound. And to illustrate that, if you had half a pound of hydrogen and antihydrogen particles, which is what, 200 grams? Half a pound, give or take? So 200 grams of that fuel, you could generate as much energy through their mutual annihilation as a 10 megaton hydrogen bomb. And that's about as powerful as thermonuclear devices get up to there. That's enough to annihilate the city of Toronto. So you could do that same amount of damage with half a pound of this material. So that unfortunately is why antimatter research makes a lot of people nervous. They think, oh my God, bombs, you're going to destroy us all. But of course, even though a concept study that was done in 2001 said that using a relatively small amount of propellant, that an antimatter rocket could reach half the speed of light and get to Proxima Centauri in just 8 years. And NASA's Institute for Advanced Concepts is also pursuing research in this. And they too said that this would be a entirely respectable idea for missions to other planets in the solar system and also for interstellar missions. But for an interstellar mission though, again, the main problem here is the cost. You need much more fuel. And some people have done the calculations on this. So Robert Frisbee, he did a study in 2003 in which he said that a two-stage antimatter rocket similar to Daedalus or Icarus would need 815 metric tons of antimatter, matter, and antimatter fuel to get to Proxima Centauri in about 40 years. And based on whose estimates you want to consult there were two studies done on how much money it would take to generate that fuel. A 1999 study said $62.5 trillion to produce a single gram. Yeah. And this plan called for metric tons. But a 2006 study said that, well, it could be done for 25 million a gram. So there you go. However, to put all of this in perspective here and allay people's fears about antimatter being a big threat, currently the total amount of matter and antimatter that have been used for organizations like CERN to do particle research, they've generated less than 20 nanograms. So 1 millionth of a gram there times 20 is how much antimatter we've produced. So that's not something that's going to be happening anytime soon. A lot of promise there, but yes, first we'd have to tackle the monumental problem of just creating the amount of fuel needed. So here too, like the fusion concept, an idea was proposed for a spaceship that could create its own. And it was known as the Vacuum to Antimatter Rocket Interstellar Explorer System, which, again, picture of that here. And as you can see, there's a massive solar arrays on the side, and what those do is they provide energy to the powerful lasers in the middle, which then are used to create antimatter from the vacuum of space. Those lasers compress matter there, around it there, hydrogen, and cause the annihilation of the particles there in the center of the laser beams there. And this the antimatter itself could be procured from radiation fields like the Van Allen belt around Earth or radiation belts around gas giants. And in theory, that idea works. You could have a ship that could produce its own propellant and reach very high speeds, but it would take quite a while in order to harness that amount of fuel. And the cost of creating the Starship itself would be prohibitively expensive. There hasn't even been any attempts to figure out exactly how expensive that would be. It's literally that high. And then you have the Alcubierre warp drive. And if you follow speculative science news there, this one is right up there with the EM drive, except that this one has not been discredited yet. In fact, it caused a bit of a stir because the idea was proposed by Miguel Alcubierre, who's a Mexican physicist, in 1994. And he came up with the idea as a way of creating an FTL concept that wouldn't violate special or general relativity. So something that could travel faster than the speed of light without actually breaking any laws of physics. And it was in 2012 that a NASA scientist, he revisited Alcubierre's equations, which were thought to be flawed. He did some revisions and said, no, that actually works out. So NASA has been studying that since, through their Breakthrough Propulsion Physics project, and more recently through their Advanced Propulsion Physics Laboratory, which is also known as EagleWorks. And they started in 2012, led by Harold Sonny White. So the basic idea behind it is that you would have a ship that could stretch the fabric of space-time before and after the ship, expanding in front, contracting behind, so that the ship would then be riding inside a warp bubble, also known as an Alcubierre metric, which would then propel it through space faster than the speed of light. But because the ship itself is not moving, simply riding a wave of flexing space-time, it's therefore not breaking the light barrier. It's not violating special or general relativity, so you don't have to worry about things like the rules of causality and so forth. So feasibility-wise, NASA EagleWorks says that the equations themselves appear sound, and a ship traveling in a warp bubble could make the journey to Proxima Centauri in about 4 years. So a wonderful idea if you could do it. However, there's all kinds of theoretical problems with it, and to say that it's strictly theoretical is a bit of an understatement there. The idea that a warp bubble could exist is possible. That's something that Sonny White and the others agreed on. But how you would exit that warp bubble, whether or not how you would go about creating an artificial one, because natural ones may exist in space, but how you go about creating an artificial one, the amount of energy it would take, it's unknown and possibly very staggering. And there's also no real knowledge on how such a warp bubble would affect the space around it, whether or not it would actually inflict harm. So they're currently researching that. They've developed a warp field interferometer to try and see if they can detect distortions produced by an Alcubierre metric. So far, the research has been inconclusive. And, another potential one, and I had the honor of, again, talking to some scientists who were doing research on this, is the idea of a halo drive, or a black hole spacecraft. And again, here the issue is cost, and there's also theoretical problems, but it is a very good idea in theory, and it's something worth exploring there once we can find a way to do it in a cost-effective way. So basically, if you could create an artificial singularity, a tiny, tiny little black hole that would measure just a centimeter and would have a mass of several thousand solar masses just concentrated in there, it would release enough Hawking radiation to power a spacecraft and power thrusters. So it would be a very, very good power source if you could maintain it and if you could keep it in some kind of field there to prevent it from just completely consuming the ship. And the only problem with that is the idea is that this would be created through the use of focused gamma ray lasers, which firing on a tiny volume of space would cause the buildup there of enough mass in a tiny little area to essentially create a little black hole. The power needed for that, though, is beyond anything we can fathom, and yes, the technology for building and harnessing a black hole is beyond anything we're capable of, so that's something to explore later. Another idea, though, was now black holes, based on the fact that they have accretion disks around them, in which particles are accelerated to incredibly high speeds. If you could park a spaceship in the accretion disk of a rapidly spinning black hole, it would achieve the ultimate gravity assist. It would be accelerated up to relativistic speeds. And once you exited the accretion disk, then you'd be able to travel to nearby star systems there in a very rapid way. And Freeman Dyson actually proposed something like that back in 1963. He said you could use stars as gravitational machines, and especially binary stars. And that idea there was, to get a gravity boost. So Professor David Kipping of University of Columbia, he said that with similarly, you would have you'd use a black hole in the same way. You pick up a much more significant boost. But there's still the massive problem of having to get to a black hole, developing the right kind of equipment there so that you could now be able to exit the accretion disk in time and, going in the right direction. Basically, the challenges of that are immense. Again, nice idea, but nice work if you can get it. So, last, I want to mention some of the people who are actually advocating for continued research in this. Many of the projects that were established over the years, over the decades, especially during the height of the space race, they were since abandoned due to funding, due to the fact that technology was not advancing fast enough. And a lot of that work has been picked up in recent years by other organizations. Now, I already mentioned Icarus Interstellar. Another is the Tau Zero Foundation. And they're named after the book by Paul Anderson there, Tau Zero, which is about an interstellar voyage that takes place. True story, I attempted to buy a copy earlier this evening, just so I'd have a chance to show you the book itself. However, it's very hard to get. It was written in 1971 and it's currently out of print. So, still waiting on my copy. In any case, this group was founded in 2006 and they are dedicated to interstellar research on interstellar flight, and they have multiple people who have joined them from NASA and the European Space Agency, and who were once part of other research projects, which once they were canceled, they joined people like the Tau Zero Foundation, and that includes Mark Willis. He was the head of NASA Breakthrough Propulsion Physics until 2002, when it was canceled due to budget cuts. And they're continuing to pursue a number of different concepts for interstellar flight, many of which I mentioned here. Another member that they have who's worth mentioning is Paul Glister, and he maintains a very good website called Centauri Dreams. If you go to centauridreams.com, he talks about deep space news research, and he's got a very good list of the different concepts that have been explored over the years. And next, yes, the 100-year Starship. These guys too also made the news, especially when the news of the Alcubierre drive and NASA picking it up broke in 2012. And they were established in 2010 as a result of NASA's Atlas Research Center and DARPA. They came together to make a grant to this foundation there. And it became known as the 100-year Starship. And their purpose is that they would be fostering the development of technology and also research into possible means of making an interstellar travel happen within the next 100 years. So their goal is that by 2110, that there is an interstellar craft that's built that would rely on available technology that could make a journey to some of the nearest stars in a respectable amount of time. So, well, that concludes our brief run through of all the available means, all the ideas that have been explored over the years. So, as I said at the beginning there, it really comes down to two big questions there. If you're talking about how, when, or can we make a journey to another planet, to another star system, there is, yes, the two questions are, how long are you willing to wait? So, are you okay with a mission that would take thousands of years? If so, great, we got lots of options. If not, if you're hoping to do it within our lifetime, how much are you willing to spend? Because there too, getting all the technology, getting everything to the point where it's at the starting line there would be very, very expensive. And when it comes to most of the ideas, they are too slow, too expensive, or they're based on ideas that just haven't been tested yet. So, as it stands, our best bet is the idea of robotic spacecraft, nothing crewed, with tiny craft that would take advantage of miniaturization, so nothing larger than a box or a small baggage cart, and most likely one that's towed by a light sail. So something that needs no propellant, has a big, shiny sail attached to it, and you accelerate that using lasers, and then you can actually reach another star system within a few decades. That's the best bet. And of course, it's, unfortunately, I should say, space agencies, while they're doing the research into this, no one is really pursuing that line of development because, again, it's just still very expensive. Any such project like that, we're talking is a small fraction of a country's annual revenue, or their GDP would need to be dedicated to such a mission. So is anyone willing to do that? Well, not quite. But we've got a number of organizations and foundations that are on it, and they have the backing of some very, very rich people. So that enough is good. It's ensuring that the research is happening. So if I were to make a bet, I would say that yes, Starshot is probably the best bet that an interstellar mission is going to happen this century. They're still very much in the research and design phase, but they are contracting out aspects of the mission there for people to submit designs for the laser, for the spacecraft. So given 20 years, they may be able to launch this mission. And 20 years after that, it would then reach Proxima Centauri, and within 4 years of that, so a total of about 45 years, we'd be finding out more about what's there. Not too long. Okay, so are there any questions? Yes?
In the beginning, you said that Voyager 1 and 2 would take 20,000 years to get to Proxima Centauri, but they're not actually headed that direction, are they?
Well, no.
And that's just a theoretical.
It is, it's just a theoretical. Pioneer 10 and 11 are. Yeah, so that's why the authors who I spoke to there, they were able to calculate when they get there. They're saying on their current heading, do the math, calculate where those stars are going to be at the time too, and is there going to be any flybys? And they said yes, that Pioneer 10 would. Just checking my notes here. Yes, Pioneer 10. Wait, one more second here. Yes, so that it would be getting to RASC 248.
38,000.
Yes, I'll have to get that. Yeah, and Pioneer 11 would be making it to Proxima Centauri. Okay, anything else? Anyone else? Yes?
In this miniature robotic spacecraft,
Yeah.
fraction the size of a cell phone,
Yeah.
how many kinds of instruments, what kind of data could be transmitted back, and how long will it get here?
Yeah. Well,
We learned that something that small, so that anything works.
yeah. Well, yeah, there, according to Professor Lowe, They've indicated that, well, it would have a communications array, a microwave communications array, that would send back images. So they intend to have cameras that would snap pictures of the planet. I believe they're also considering a magnetometer to measure for magnetic fields around Proxima b. They want to know if it's got its own magnetic field, which would increase the likelihood of it having a good atmosphere and possibly life. And I think a spectral analyzer, so that they can get a sense of what the atmosphere is made out of, if in fact it still does. So that's what they're looking at there, and it's a tall order, but again, we're talking about a spacecraft about this big, and it's taking advantage of all the advances made in miniaturization in the last 40 years or so. So they're at a point now where they can actually fit a lot of those instruments onto a microchip, onto a craft that big, and it would only weigh a couple grams. Anyone else? Yes?
What about the odds of something like this over that time and distance actually hitting something and never getting there? What are the odds of that?
I can't give you exact odds, but pretty good. That's exactly what they're trying to figure out. That's something that came up a lot. It's not just groups like Breakthrough Foundations or Breakthrough Initiatives that are trying to calculate, what are the odds of success here. It's been determined that, the biggest threat would be if we hit an interstellar particle like a random atom of iron, because at a relativistic speed, that would hit it with a force greater than most bullets and punch a big hole in it. So they've talked about how they would equip their magnetic sail with a protective layer that could absorb anything like that, and that would keep the sail alive longer. Again, no one knows for certain just how good or how bad the odds are of the ship actually getting there, but they've done the math that says, it's totally possible. It's just, again, you have to figure for the worst case scenarios and build the craft in such a way that it's ready for that ahead of time. Yes, but collisions are very likely. It's going to happen.
Okay, I've got a couple of questions. One is cosmic rays. If we had a generational ship that many generations to get there, your inhabitants might be all mutants by the time from all of the high energy. Has there been any ways to minimize that?
Lead shielding. There's been a lot of research into this, because just going to Mars, right, that's a big question. So there has been, lead lining, magnetic shielding is another one there. I talked to a guy who did a very interesting study. He said, have the ship generate a magnetic field around it, which could repel cosmic rays. There's even proposals to use the ship's own waste as a barrier. So in the walls, have your plumbing so that all the urine and excrement generated by the crew becomes a layer of insulation. And that way, you don't have to deal with it, and it's keeping you alive. What else? That and just other things. You want your walls thick enough so that it's like we figure we're going to be around an awful lot of radiation. Let's basically act like we're in a nuclear building here.
It seems to me that the light sail. Let's say you send something out there. Could the curvature of the light sail be used as kind of a parabolic reflector to send a signal back to the Earth to get your information back?
I haven't read anything on that there. I don't know if anyone's even thought of that. It's interesting. I might bring that up, actually, next time I talk about it.
Pardon me?
You might want to do that now before I steal it.
Well, it's really quite a thought-provoking talk you've just given us, Matt, and the stars are closer than I thought. If we're talking maybe 100 years or 1,000, rather than my back of the envelope calculations was 50,000 years. So wow, that's just down the street.
I myself was very encouraged by just what I've heard in recent years there, like just the number of people who are working on this, their own enthusiasm, right, their own dedication to it. It's like, these are scientific minds, so you're inclined to think, yeah, they know what they're talking about. And this thing, this is doable, you just, gotta keep working at it, and the funding needs to be there, but, it's like, the interest is there, so all long enough time period, long enough timeline, it's like, yep, we could do this. We could send a mission. We might not all be here when it gets there, but that's okay. At least you got Martin.
So I'm just wondering your opinion on this one. So I've always thought, when you consider we've only been flying for 120 years,
Yes,
and look at where we've gone,
yes.
we're accelerating so fast that in 200 years from now, a couple of generations away, this is gonna be, so insignificant, this level of science we're operating so much further ahead.
Yeah,
Why do we waste our time on it now? Why don't we work closer to home on improving the science and developing this technology, rather than spending the astronomical amount of money on a test? Is there a value in really doing this versus just knowing that we're gonna get there?
yeah. Well, yeah, absolutely. I agree with that, and I think that's probably how it's going to turn out in the long run. The work we're doing right now is probably going to be just, a proving stage for what comes along later. And it's kind of already happened in a way too, because it's like the research that's going on today is building on a foundation established from the late 50s to the 70s. All this lucrative research was done that basically was like, how could we get there? And they were sort of stopped there because all these studies produced, it's like, yeah, it's doable, it's just really, really, really expensive, it would take a long time. And now we're that much closer. It's like, well, we've now realized this level of development, and we are revisiting the ideas. So we may send out some precursor missions in the near future, and they would probably be little light sails, little tiny star chips. Within that's you got me thinking of the whole idea of the technological singularity. Right? That idea that, all this advancement, all this development, there's going to be a huge explosion in what we can do. We can't possibly imagine what's going to, the next 50 years are going to be like after it, right? So it's like, we probably can't even begin to imagine what the future is going to bring or what's going to be possible. We could end up in a situation where we're like, oh yeah, Halo drive's easy. Just, get together a bunch of gamma ray lasers and shoot a spot and boom, we got a reactor. So let's go. Yeah, and that's, a lot of the research there for the theoretical concepts, it's depending on that. It's saying, this could be doable if this level of technical development happens, and it's entirely possible it will.
Zach,
Yes. Artificial intelligence, yes. Oh, I see. A ship that's guided by her. Yeah. Well, no matter what. It's a good topic. In fact, a research friend of mine there, we did a work on this about AI and the applications it would have, and my part was contributing for space exploration. And any mission in the near future there, be it interplanetary or interstellar, is likely to use a certain degree of AI, just because it's like, why wouldn't you? If we have a machine learning core at the center of a mission there, if it's capable of absorbing all the streams of data that it's going to be gathering on the way and making, interpreting it, making those decisions, of course you want that there. You don't want to leave this up to people back home who are going to be hearing about, something years after it happens to the ship. So any mission that goes out, even in the next few decades, is going to have some kind of AI in it. And it's going to be responsible for taking all the massive volumes of data that goes into a space mission and making decisions on the fly. So,
that's a great point there, Nathaniel. Many of the people in this room were traumatized about 3 lectures ago by a talk on AI, and we didn't realize how advanced that was.
I
Before we go, I've got a question as a science writer.
Mhm.
It's fascinating, these things that you've researched here. You must have taken a lot of time to dig into this. Do you, as a science journalist, get to choose your own topics, or are they presented to you? Sure.
Yes and no. For Universe Today, I'm writing for them full-time since about 2014. And most of it has to do with news or general knowledge articles there, right? So I don't really choose what I'm covering there, but yeah, a lot of times I've done series articles and stuff that myself and the publisher agreed on. Like, let's talk about terraforming. Okay, so series on terraforming. How do we do Venus, Mars, the Moon? Where else? And can we? For interesting engineering, though, it's been it's me and my publisher. We talk about what do we want to cover.
Wow.
Shoot ideas and then get into it, and then that's how I've realized what I love to talk about. It's usually interstellar travel or terraforming or the history of.
Okay, well, listen, as a token of appreciation, we have a coveted T-shirt from the Victoria Center of the Royal Astronomical Society for you. So thank you very much.
Thank you so much.